Hello, I'm Mark, and welcome back to my Unreal Engine tutorials on how to add support for wheeled vehicles in your physics movement component. I think we're in the final stretch here of the wheeled physics vehicle simulation videos. I think we've got only two more left, this video and the next, and we'll be dealing with wheel friction. So as a quick little recap of what we've covered in wheels so far, we created a component or we created some code to help us with center of mass, so we can kind of get this vehicle to kind of look like it's bouncing around a little bit more on the suspension. We had created engine and transmission simulations so that we could take the accelerator inputs and turn that into angular positioning and angular velocity on the wheels. We went ahead and did some animation work so that we can reposition the wheels as we're kind of going over the terrain to make it look and feel like it's bouncing along when we implement the steering and the suspension work. And then finally, I think we finished off with suspension simulation, and that was definitely a very lengthy topic. But that kind of also is now setting us up for the final for our final video, which is now dealing with wheel friction. So that is going to be taking that angular position and angular velocity of the wheels and turning that into thrust so that we can accelerate our vehicle across the desert as seen here, as well as brake and stop our vehicle as like so. And so what we'll be doing is we'll be working on code that'll allow us to, again, speed up, slow down, as well as, and this should also work in for the angular positioning as well. And we'll also be putting in some code to help make sure that we account for both front-wheel drive, rear-wheel drive vehicles, as well as all-wheel drive, as seen here. So, as always, we have a lot of ground to cover today, so let's get started. Okay, so I think the best place to get started is within our wheel simulation setup. So, as you can see, we've been working on this for a little bit. As we've been kind of going through a lot of the other systems, they all seem to want to come back into our wheel, which is where we want all of the simulation magic to happen. So as you can see, we've already got some parameters in here that we are needing to help support everything from our suspension systems to our steering systems. So now I think we're in a point where we can start to finish, kind of fill this out with all the missing parameters that we need in order to create wheel friction. So first off, let's start with the parameters. So what we have here is we have wheel radius, wheel width, we've got steering enabled, and let's see, I am going to bring in, I think what we're missing here is going to be, so after steering enabled, I'm just going to go ahead and add, we need brakes, so we have the ability. We've got the ability to speed up, but we also need to have the ability to slow down. So each wheel is going to have a brake. Have the ability to have brakes if we wish to turn braking on for those wheels. And to do that, we are going to add some additional Boolean checks to that. So we have max brake. So this is the braking. This is kind of like the wheel brakes, and then this is the handbrake torque. So depending on how you want to set this up, if you want to have differences, if you can set that up as them being different, or you can give them the same value. It's up to you. But yeah, this is going to be the controller, the analog controller, where we kind of start squeezing the brake in order to apply the brakes, where the handbrake is kind of like the, I guess on more modern cars is that, you've got a button you press and it turns the parking brake on, turns the parking brake off, but in some of the older vehicles, you've got that ratchet system in place where we can actually, create a different set of torque. So that's kind of why the handbrake here is kind of separate from the max brake here, if you want to do that kind of setup. Let's see. We already have the axle type up here, so this will allow us to define whether we're front wheel drive or rear wheel, or if it's a front axle, drive axle, or a rear drive axle, and that will play into our traction control system. But we are going to also need wheel friction. So let's bring those parameters in. So again, this is the wheel surface in contact with the materials that we're going to be driving across, right? So I'm splitting this up into two, because what I'm also going to be doing is when we do the ground trace, we've set it up to get the surface friction of the material that we're driving over. So, and the way that wheel friction works is there's really every tire or every wheel, right, has a friction value for the material that tire is going over. But because we may have different types of tires for different vehicles, we kind of wanted to I kind of want to split that value out, and so that's what we're going to be doing here between the wheel surface friction and the multiplier and the ground friction. So the ground friction is going to be a constant value. So that's a friction value. If it's got grip, you're going to set it to 1. If it's slick, then you'll set it to less than 1. And then the surface friction, wheel surface friction, is going to then either be added or multiplied. I think I'm adding it together so that we can then create a tire friction for that surface. And then the wheel surface multiplier is then taking the friction value and then multiplying that across the surface of the wheel that is in contact with the ground. And so that's how I'm going to be calculating that. Then next is cornering stiffness. So this is our lateral slip. So if we just use friction alone to try and keep our vehicle on the ground, that's going to allow so the wheel friction is kind of working to generate thrust to get us forward or back, starting or stopping us. Cornering stiffness is the lateral friction. So this is kind of where, so if we have a vehicle in which we need to stiffen it up so it doesn't slide around as much, we can control that through adding more cornering stiffness into the vehicle. We can also use lateral slip graphing if you want to do it this way. So we'll actually have two methods. I'm not going to go into the graph quite so much. I'm just going to focus on cornering stiffness, but the idea being is you can either use cornering stiffness, but if you wanted to then create some kind of a lateral slip graph instead, based on the speed of the vehicle and the slip, and its ability to skid sideways, you could do that through the lateral graph, and then you've got the multiplier here again so that you can scale your graph accordingly. And let's see, and then finally, let's just bring all three of these in. So then finally, some additional values we can play with. We have a side slip modifier. We also have a slip threshold and a skid threshold. So again, this is more for tires slipping and gripping as they're in contact with the surface. So if our wheels are, if we have a slick surface and our wheels will start to get over a certain threshold, right, they'll start to spin on that surface versus trying to keep in, moving with the surface. And then we have this spin rotation as well, max spin rotation, and this is more for the animation of those wheels. All right, so now that we've got all of our parameters that we need to finish off our wheel friction simulation, we can now move over to functions, and we're going to need a lot of them. So before I get to functions, what I'm going to do is I'm going to come down to private variables. So what we have is we have these public variables up here, or protected variables. These are the variables which we'll be able to set up in our blueprint. And so this is kind of like how we want that, that tire simulation for that specific wheel to work. The private variables here, this is the actual data which is going to be working data within the simulation itself. So, on initialization, we'll be setting this up, and then as the simulation drives, we'll be able to get our angular position, our sting, which is more for where our wheel is rotating, and that's really more for animation. Steering angle, again, if it's a wheel that steers, how much angle does it have? Mass per wheel is good, useful in the calculation. Drive torque, this is the maximum amount of torque that is sent to the wheel to get it to turning. Omega, and then we have our again, our dynamic wheel radius. So if you wanted to have a wheel which may be changing in size, you can we can take the actual size, and then we can start to affect that if you wanted to. But we are going to need a lot more variables in here, so let's go ahead and start adding those in. All right, so I'm gonna be breaking this up into like small little subsections, so you can kind of get an idea and kind of group them all together. So we've got dynamic wheels, we have omega, so I'm also going to go ahead and add in the inertia. So as the vehicle's moving, it's got its own energy as well. So we also need to make sure that we're calculating the inertia of the vehicle and adding that into our tire simulation. We're going to need drive torque, but since we're also going to be adding braking in there, we're going to need, as well as our suspension system, we're going to need quite a few other variables in order to calculate that. So I'm just going to bring those in, and these are the units that these surfaces are going to be in, so you can kind of get an idea of how this is going to be calculated. So what we've got is this is the drive torque, so this is the amount of torque that's pushing. This is the brake torque, this is the amount of torque that's going to be stopping us if we apply the brakes or the handbrakes. Force into surface, this is gravity that is pushing the wheel into the ground. So if your wheel is in contact but you don't have that much, your vehicle's is kind of separating from the ground, if that surface pressure gets less and less and less, that's going to affect the amount of grip on your tires. So we'll be looking at surface, force into surface, ground velocity, angular position. We already have that, so let's just make sure. And angular steering, I'm just going to take these out so we can get rid of the dupes. Surface friction, this is, again, this is the amount of friction that is on the surface, because we're going to be breaking that friction coefficient into two parts. And then we have the wheel surface. So this is the amount of actual surface area that is in contact with the ground. So force into surface, again, let's just go ahead and just remove that. Then we have a force friction and mass per wheel. So I think we're missing force friction. So let's go ahead and add that one in. I'm just going to put that there and there. And then, oops, let's just put a little bit of contact in there. So we have the in contact value. So our wheel will be based on all the information. We do need to set this flag. Again, if the wheel is in contact, it's going with the ground, it's going to do one set of code. Otherwise, if it's not in contact, it needs to do something else. So we'll just leave that variable there. But we're also going to need, and I'll include these notes as well. So we're going to need the slip angle. So this is the angle. This is the angle between the wheels forwards and velocity vectors. So that's our slip angle. And we are going to need engine braking. So this is the value. So this allows us to turn engine braking on and off. So if this is a powered wheel, then engine braking will affect the wheel, right? Versus if this is a wheel that is just freely moving, so it's like a wheel on a trailer, right? Then that wheel's not going to be affected. So again, we can turn this variable on or off and add that into the simulation. Let's see, applied linear drive, brake. Yep, I'm going to need all this too. So this is the applied linear drive force, applied linear brake force, and then the available grip. So this is a very important one. This is the available grip that we have to work with, and then we have the input forces here. So these are, again, this is everything that we're going to be calculating per tick during the simulation, and that's per physics tick, not game tick. All right, so that's all the variables. So now I think we can kind of come back up to the protected functions. Are these public or protected? Oh, they're public. So these are all of our public functions. So let's go ahead and start to fill these out. Actually, you know what? I'm going to start with the private functions first, and then we'll work to public. So for this, I'm splitting certain functions into private. So the private functions are going to be used within our simulation function. Again, just breaking some of that simulation code into smaller pieces makes it a little bit more easier to digest as well, and a bit more manageable. So I'll just be bringing all the functions that we need for this video. So we'll be calculating the available grip, and again, we need to calculate that on per tick. We'll be getting get the final longitudinal force. So this is the longitudinal forces on the wheel, which is going to force us, which is going to get us to accelerate or decelerate. Lateral forces, these are the forces for keeping the vehicle from skidding. Yeah, this is check clipping. So we want to take a look at the size of the tire and make sure that we've got the right, and we're going to be applying the right amount of force across both the longitudinal and lateral. And then we also have apply slippage. So if our vehicle is exceeding a certain tolerance, right, then the vehicle will start going into slipping versus traction. So, and that's kind of what we have there. So we'll be calculating all that within our simulation. All right, so now let's come back up to our private functions, and we're going to have a lot of these public functions, I should say, and we're going to have a lot of them. So just bear with me as we try to get these out, and then once we've got all this, then we'll go over to implementation. All right, so we have the, let's see. Just double checking my work. We have get effective radius, but we don't have a setter, so let's get the setter in there. So we have set wheel radius, and we have we have the get effective radius. Again, this is just going into the dynamic wheel radius. So I'm just going to try and group these together. So we have the getter and the setter together, working on the same positions. We have set angular position. So we've got a set and a get. This is on our angular position. Again, these are all private variables that we're working with. We've got set angular velocity. So I'm just going to go ahead and put that one down there for now. And I'm also going to add the set matching speed. So again, this is going to be omega based on the linear meters per second, which is going to be coming in as, and then dividing that by the wheel radius. So this is if we have a wheel that doesn't have power versus a wheel that does have power. We're going to want to set that wheel if it's in contact with the road to kind of match wheels with power. So it kind of keeps things a bit even. We've got set braking torque. So again, this is our ability to set the braking torque. So that's going to take a value, and we're going to check to see if we have engine braking on there. We have set driving torque. Yep, got that. And we have the get driving torque. Gonna have a set braking torque override, and we're also gonna have one for driving torque override, and I'm just gonna move the driving torque override up with the driving torque. Try and keep these things together. Let's put that there. So, oh, actually, you know, I don't think we need this one. Yeah, we don't need this one. Not going to implement that feature. Set ground torque speed. Let's see, where should we put that? Yep, that one can go there. Set wheel load force. I think I have set wheel load force. We've got that. Set surface friction. Yep, we are going to need the set surface friction. I'm going to put that one up here because they're kind of used together. So this is usually where we're going to be getting that value when we actually do our... So this value will be created when we do our ray tracers into the ground. We can get that information. Set on ground. Do I have set on ground? Yes, I do. Set steering angle. Yep, got that. Set mass per wheel. And I think we have mass per wheel. All right, so now that we've got all the setters, let's go ahead and get all of the getters, the matching getters for this. All right, so first up is get force from friction. And I'm just going to go ahead and put that down here since it doesn't have a setter. So this is getting the force from friction value, and this is going to be coming back as a vector. So what we'll be doing is we'll be calculating this as a vector, and that vector will then come back, and that's what we'll be using for the amount of force based on the friction value that's going to propel our vehicle forward or prevent our vehicle from moving. Let's see, effective radius. I think we already have that covered. Position, angular position. Do we have any? I think we have a set angular position. Yep. But we don't have a set angular velocity. So let's go ahead and put that one there. Or get angular velocity. So there's our. So we have a getter and a setter for our angular data. Get wheel RPM, I think we have that up there, so we don't need that. In contact, we already have. We have a couple of is variables for is slipping and skidding. So I'm just gonna pop these guys down there. So this is getting the slip magnitude and skid magnitude, and we're gonna go and get those functions a little bit later. But as you can see here, we want to know, are we slipping and are we skidding based on the magnitude, and if that magnitude is over the threshold, it'll let us know if we're skidding or slipping. Get steering angle, I think we already have that. This one is the get normalized lateral slip. So again, we're going to need the slip angle, and we're going to do a quick little calculation on there, clamping it between. So we want the slip angle, we want to take it from radians to degrees, and then from there we're going to then divide that by 30, and then so that's everything within here for the clamp, and then we're going to clamp that between 0 and 1. So if this is anywhere between 0 and 1, that's kind of where we want it to be. So that's get normalized lateral slip. Get wheel load friction. Do I have a load friction? Probably not. So let's just go get that. This is force into surface. Do I have anything? Do I have anything already for that? Nope. Just put that there. And I do have a get surface friction. So So we have a set surface friction here, so I'm just going to group these two together. So we have set surface friction and get surface friction. And then as you can see here, we also need to be able to, I'm going to create two getters for slip angle. Do I have a set slip angle yet? Don't think so. We're calculating it anyway, so we just need to get the slip angle. Get drive torque. I think we have get drive torque. Yep, so we have a getter and a setter for the drive torque. I think we have a getter and a setter for the braking torque. Let's see. Drive torque, angular position, surface wheels. Nope. Alright, so let's go ahead and get the braking torque real quick. And then road speed, and I'm just gonna bring all these in. Alright, so road speed, this is getting the road speed, which is the ground velocity at x. So here we have the vehicle ground speed, right? But road speed is only in the x direction. We don't care about the y direction. So then we have the get wheel ground speed, which is again the omega times the wheel radius. And then we have the slip magnitude. So this is the, as you can see here, is are we slipping? So this is the wheel ground speed minus the road speed. And then what we have is we have the skid speed. So slip speed is are the tires slipping in the x direction, right? So if the wheels are going faster than the amount of friction force that we can keep, then the wheels are going to be slipping instead of gripping. And then skidding is left and right, so that's just the ground force, the ground velocity vector on the y plane. All right, so that should set us up for all of our private or public functions. So the only other thing that we have, so we have the initialization function here. So the only other public function I need to add is our simulate function, and this is the function that we're going to be using to actually run our wheel friction simulation on each wheel. Alright, so now that we have all of this, I think what I'm going to do is I'm going to go ahead and just, so you can see here, a lot of these are just getters and setters, so we're just going to keep them in line. We do have a couple of functions here which are going to require us expanding it, and I think we also have a couple of functions here which we just need to add to, so we'll go ahead and do that in the implementation file. So let's go ahead and move over to that real quick. Okay, so in the interest of time, I just went ahead and just created these functions and just moved them over. Again, we just fixed the green squigglies, and that should then generate all of the functions that we just need to add. So they're all here, so we could just go ahead and add the implementation in. So for set wheel load forces, we already did that one when we were doing suspension, because we needed to know whether our suspension system is in the wheels on the suspension system are in contact with the ground or not. So that's done here. So, and we don't need to add anything else into it, so we can just skip over this one now. So that's set up. So next on the list is set the brake torque. So what we're going to do is, see, it's taking two variables in, so let's just add those in. So again, we're just setting the brake torque, which is over here, brake torque. And I'm just going to go ahead and just close that. And we also have is engine braking. So again, if this wheel is tied into the power system, it will then also add that in as well, or tell us if this is an engine braking value or not. Next up is the set brake override. You know, I don't think we need this one, so I'm just going to go ahead and I'm going to come back over to here. I don't think we need the set brake override. Just going to remove that real quick. Yeah, we don't need this one. We're going to calculate available grip. So let's go ahead and get that done. So let's see, where have I got that? So calculating available grip is here. So it's going to be a rather long equation. So again, so the available grip is going to be going in, is a combination of force into surface. Again, this is coming from the ray cat. This is actually the amount of force going in the z direction, but that is being exerted on the tire. So this is actually a value that will be coming from the suspension system. This is the wheel surface versus the wheel surface multiplier. So this is the amount of surfaces in contact with the ground times the multiplier. So we're going to need to calculate the wheel surface for each wheel, and then the multiplier. And then we have the surface friction, and I'm actually multiplying that by the wheel surface friction. So this is the tire friction, this is the materials this is the friction coefficient of the material, this is the of the tire, and all I'm doing is in this simulation is I'm just multiplying those together to create a surface friction value. You can choose to multiply it, or you could choose to add it. It's up to you. For this simulation, I'm just using multiply. Okie dokie. Then moving on to the next one, we have get final longitudinal force. So this is the force of the vehicle going in the forward and back direction. So this is going to be applying traction to our vehicle. So let's go ahead and get that all set up. All right, so let's just go ahead and implement that. So here, oh, that's a float. I'm going to just make this a double. So we have a constant here, which is the K. This is our K, constant K force. Then we have a longitudinal force. What we're looking to do is we want to calculate this longitudinal force. So we need to know either we're braking or we're accelerating. So if we're accelerating, we're just going to take the applied linear drive force that we'll be calculating in the simulation and just applying that. Otherwise, if we're braking, then we have to do some additional math. So this is the force required to bring the vehicle to a stop. So that's going to be based on the mass per wheel multiplied by the K value. And then that's going to be multiplied by the ground velocity divided, and then all of that, is then going to be divided by delta time. So this is per frame. That should then give us the final longitudinal force, which is then, so then what we do is we just take the applied braking force, right? So this is the amount of stuff that's being braked. And then we're going to go ahead and clamp that between the final longitudinal force, which is the applied braking force, not to be confused with the applied linear driving force. So this is the linear braking force, and then we're just going to clamp. So this is what we want, right? Well, this is actually what we want. So we're going to take this in, and we're going to do a absolute value of the force required to bring this thing to a stop. And we are both negative and positive. So we're going to check to make sure we're within those tolerances. If we're in those tolerances, then that's going to be our final longitudinal force. If we're outside of those tolerances, right, then it will either be this, which will be negative, or this, which will be positive. And we need to know both negative and positive because the vehicle can go either forward or backwards. So if we're in reverse and we hit brake, we need to make sure that we are still going to be braking in the reverse, or if we're going forward, right? So we need to make sure we're within both a negative and a positive of that. And then ensure the brake, the brake opposes current direction of travel. We've got the current direction of travel, which is our ground velocity on the x. And as long as we are greater than 0, if we're 0, technically we're already stopped. So if we're already stopped, we don't need to do this. Otherwise, we need to take the longitudinal force. So all we're going to do is we're just going to make sure we take the longitudinal force, which is this guy, and multiply that by -1, which will then give us the counter force to the direction that we're going in to get us that longitudinal force. So, yeah, that's how we're going to be calculating whether we need to accelerate, decelerate, and what forces are going to be needed to do that. All right, I'm just going to go ahead and just close those real quick. All right, so now we have get final lateral forces. So this is the ability to keep us in a straight line when we're turning. So this is how we're going to calculate whether we're going to be slipping or skidding going into a corner. All right, so I'm just going to put this in, and we'll get rid of the extra return value. All right, so again, this is lateral forces. This is what's going to keep us going. This is what's going to prevent our vehicle from skidding out, or maybe not, depending on how you want to set things up. So again, our K-force value, that's a double. We have our final lateral force. We have the force required to bring to a stop. Again, we still need to calculate that. And again, that's per tire. So it's the same calculation that we're doing really up here. Is that we're doing down here. Again, we need to know this. Again, this is now on the lateral versus the front to back. And then we have the lateral slip and grip. So this is our lateral slip graph. So if we're using the slip graph, then what we would then do is we would take the slip angle, multiply that. Well, if we're not using the slip graph, then we're going to take the slip angle times the cornering stiffness. So that's the cornering stiffness value. If we are using the slip graph, then what we're going to do is we're going to take the value coming off the graph and convert that from radians to degrees. And then we're going to then multiply that by a lateral slip multiplier. So again, this is depending on how you want to set up your graph. So if your graph is already in degrees, then you don't need to worry about. Well, actually, we do need to take the slip angle and turn this from radians to degrees, and then your graph would technically be in degrees, since that's a bit easier for us to kind of plot. And then we would then take the lateral slip multiplier, right, and in order to calculate that value. All right, so and then that should get us the lateral forces. So then a lateral force, if the lateral force is greater than the force required to bring to a stop, then we'll take the bring to stop and make that the lateral force. Otherwise, if it isn't, we don't need to worry about it. Then we're going to check the ground velocity. If ground velocity in the y direction is greater than 0, i.e. we're moving and we're not at a standstill, then we'll take the lateral force and multiply it. So again, this is the force that we're using to keep the vehicle from sliding out. So again, we're creating counter forces in order to keep the vehicle moving forward in a straight. So if we turn, right, we don't, unless you want to set up your vehicle to skid out. And again, that's why we have the ability, cornering stiffness or the graph, right? You can then set that up, and that can be done on each wheel as well. So it's not like we're setting it up for the whole vehicle. We're just setting it. We can actually set this up on each wheel of the vehicle. All right, so that is how we're going to figure out how much force we need to keep in order to keep our vehicle from skidding out. All right, next, I'm just going to go and minimize this. We're going to check for clipping. So we'll go ahead and do that real quick. Just 1 second. All right, so this is how we're going to be checking for clipping. So again, we need to go. We'll be taking, getting some calculations based on the final longitudinal force plus the final lateral force, and that's going to give us the force squared, yeah, the length or the length squared, right? So that's the area. And then we're going to then take the area squared and or the length squared, right? And we're going to then see if it's greater than 0.05, and then from there what we have is then we'll take this, get the square root of the length, and then we'll take the available grip, and this is the available grip to our tire, and we're going to divide that by the length to get our clip value. If our clip value is less than 1, then we're going to then, if a clip value is greater than 1, we don't care. We're not going to do any of these modifiers. Otherwise, if it is less than 1, then we'll then say, okay, are we braking and are we not engine braking? That's pretty much to check to see if our wheel is actually locked up. If it is, then we'll set our wheel lock to true. So we're actually locking the tires versus letting the tires kind of, slow down naturally. And then we also have the final longitudinal force. So again, we'll take the longitudinal force multiplied by the clip, as well as the final lateral force multiplied by the clip, and then our output final longitudinal force. Again, this is the side slip modifier, and this is side slip. So this is longitudinal and lateral by the side slip modifier and the side slip modifier. So all right, so that's our clipping. So finally, we're coming down to the last 3 functions. So we have apply slippage. So we're applying both grip, but we also need to figure out if we need to apply slip. So slipping, a tire slipping, and you might see that when we actually run the simulation when we first start driving. If I stomp the wheel, if I stomp the my finger on the gas, right, on the gas trigger, the front wheels may start, if they don't have enough pressure, right, ground pressure, they may start, those drive wheels may actually start to slip a little bit before they bite into the ground. So that's kind of what we're going to be calculating. So as you can see here, we have the slip omega. So what we're going to do is we're going to take a look at excess torque. If there's any excess torque in the system, we'll then divide that by the inertia and then multiply that by delta time. And that should give us a slip omega, and then the slip omega, we just want to make sure the slip omega is between the min and the max spin rotation. Again, this is going forward or back, depending on which way the vehicle's going. Right. We're going to see if the wheel is locked, then we want that omega to pretty much come down, pretty much decelerate very, very quickly. So we'll just take the omega and multiply that point by 90%. And that should then, which is 0.9, and then that should really bring the omega down very rapidly to simulate wheel locking and skidding, which would then give us a slip or a skid. Versus, if not, then we're going to check to see if we're in contact with the road or not. If we're in contact then with a surface, then we're going to then take the ground velocity and divide that by the dynamic wheel and a kind of small number. If this, so we want to check these two numbers, and that'll give us the ground omega. And then once we have the ground omega, then it's pretty much omega ground omega minus the actual omega plus the slip omega, and then that's just a plus equals omega, right? So again, this is an additive process. Otherwise, if we're not in contact, then we're just going to use the slip omega, and then this. So if we're not in contact, then the idea being is that the slip omega should technically be a negative value. So this should then allow our wheels to start slowing down if they're not in contact and they don't have any excess torque, right? All right, so that should handle slippage, whether we're slipping in the air or slipping on the ground. Okay, so next is going to be our initializer. So we started doing the initializer when we were working with the suspension because we needed to make sure we had the wheel radius and the dynamic wheel radius. So now we can kind of finish this one off. And the only two things we need to do here is setting up the inertia. So this is our wheel inertia. So again, we're just going to take the mass. So we're going to halve the mass, take the mass of the wheel, halve it, and then we'll just then take the wheel radius and square it, and then that should give us the inertia. Again, because the wheel has mass. And then we have the this is the wheel surface. So again, I'm calculating that by just taking the wheel radius, multiply that by 2, and then multiplying that by the width. So this gets me, and then all I do is then I just multiply that again, or divide by 3, to then get me how much surface area is underneath that wheel. So that's how I'm calculating that. Alright, so now that we've got all of the building blocks in place, we can now come down to our simulate function so that we can simulate all the magic in creating those wheel frictions forces. Okay, so now we're in the simulate function, so let's go ahead and get this thing going. So first off, we're going to need the slip angle. So, and as you can see here, we have another utility function, so let's go ahead and create that. So we need to be able to calculate the slip angle based off the ground velocity and the x velocity. And we're calculating this up front because we're going to need to know, based on the last tick, what the new slip angle is, based on our velocities on the y and the x axis. So let's go ahead and do that real quick. So let's go and find our utilities function. So physics simulation utility. So as you can see here, we've been kind of building out some utility functions. These are just static functions that we can use to either create some very simple calculations for scaling. So we'll just go ahead and add this in here real quick. Alright, so calculate slip angle. So I'm just going to add this in here, and let's see if Visual Studio is going to put this in the right place. Alright, so there it is. So now let's go ahead and get the implementation done. So what we have, we've got two doubles coming in on the y-axis, on the x-axis. So let's go and add that. And I'm just going to drop this in here. So again, what we're looking for is a value. So, and we have a constant here, which is our lateral speed threshold. So this is a constant. You could make this a constant if you want. So this really isn't going to change, but this is the 0.05. And so then what we're going to do is we're going to take a look at the y, which is us going skidding, right? Or if we're going to be skidding. So this is the forces going in the y direction, and it's going to see if it's within the tolerance of the lateral speed threshold, which is 0.05. If y is in that tolerance, right, then we'll take, okay, let's take a look at the y and the x, and we're going to just put that into the a tan 2 function here, and that is off the math struct. And then we'll then get the absolute value of that to get a value. Then we'll take that value, if that value is greater than half pi, so I'll just, that's what that is. So if it is greater than that, then what we'll then do is take the half pi, or take the pi, I should say, not half pi at this point, and then minus, so we'll take pi minus value equals the new value, and then that's going to come in, and that's going to calculate our slip angle for us. And of course, if y is greater than this, then we'll just take a slip angle of 0. So alright, so that's in our utility. Let's come back to our simulation. So that's the first thing that we need to calculate, setting the slip angle based on our last ground velocity and our last on the y and the x-axis. Alright, so next we are going to go ahead and set the applied driving and braking force. just going to add those two in there. So that is going to be the drive torque and the brake torque that's coming in as inputs, right? And we'll be doing that in the next video when we kind of integrate that in all of this into our component. And then this is the dynamic wheel radius, which is our wheel radius, our current wheel radius of the wheel. And so that's going to give us the linear braking and linear drive forces needed to move our vehicle along the x-axis. We are going to need to know how much available grip we have, and again, this is being calculated. Again, we're calculating this per tick, so here it is. And the reason why we want to do this is that if we're on a vehicle which is going across different surfaces, then we need to check to see which surface we're on, to determine whether we still need to have that same constant grip or not based on that. And so again, this is where you can use, as we're doing the tracers, we've turned it on, we can take a look at the material underneath the vehicle. And so if you're working with your materials team to kind of create new materials, you can give a different friction value in there. We can pick that up and apply that to kind of give vehicles a different feel. And that's again, this is happening per wheel. So if you've got one wheel on the road, one wheel on the dirt, these wheels are going to have different friction forces, which will create different forces on the vehicle as you're driving. So next, we've got some additional variables which we need to set, and these are local variables. So let's go ahead and create those. So we're going to need the final longitudinal force. We're also going to need any excess torque, if there's any excess torque being generated, and then any final lateral force as well. Is braking, so again, this is a value which we need to check. So if braking torque is greater than the drive torque, then it means that we're braking. So versus if the drive torque is greater than the braking torque, then we want to override that. So we're not braking, we're actually accelerating. All right, and then we also want to set the is wheel lock in case the wheel is going into a full wheel lock. Okay, next we are going to be checking the force into surface to figure out how we want to apply our longitudinal and lateral forces. So to do that, I'm just going to go ahead. Let's just set up our if structure. So again, we want to check to see if this is greater than a small number. So this is a Unreal Engine constant that they've defined it. So that's how they define a very, 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 very small number. So we need to make sure that this number is greater than that. If it's greater than that, it means that we're going into a surface so that we can apply the force. Otherwise, if it's not greater than that, then we'll treat it as not being in contact with the surface. All right, so first off, again, final longitudinal force, and we already have these functions. So we have the get final longitudinal force and we have the get final lateral force, which is what we're calculating up here. There's longitudinal, there's our lateral, so that's going to get us the x and the y forces. That's either going to keep our vehicle going forward and on the road, or have it going skidding off the road. Then I'm just going to go ahead and put these forces into the input force. So we're going to take each one. So this is the longitudinal, it's going to x, lateral is going to go into y. So that's our input force, and that's a vector. And then we're going to check for clipping. So again, this is going to be based on whether we're braking, final longitudinal forces, final lateral forces, and is wheel lock. And so again, that's our clipping, and our clipping is going to determine our final output. So again, so this function is using an ampersand, so we're putting forces in and we should be getting those forces back out again. So that's kind of what's going on here. So that's why this function doesn't, it's not returning one value, it's actually returning the final values for this, this, and this. So so it's just a void function. All right, so if we're not in contact, or if this wheel has no force on the ground, then we're going to do this instead, which is just going to check the omega. So this is the max, check if the max spin, if the omega is less than the max spin rotation, then any excess torque, then drive torque is excess torque. So this could be that it's a powered wheel. So if it's a powered wheel, we want that wheel to keep spinning. If it's not a powered wheel and it's not in contact with the earth, then we want that wheel to slow down based on the wheel's inertia. And again, we're going to run the clipping function. But this time, since we're not calculating these values, these final longitudinals will be 0 and 0. And then again, we're just checking to see if the wheel's locked and if it's braking. So we want to check for clipping in both, whether we're in contact or not in contact. All right, so now that we've gotten our forces, now we need to see if if those forces are going to be exceeding tolerance or not. So this is our apply slippage. So again, we're applying the slippage, and we're going to say excess torque delta time. So we have the excess torque, any delta time is wheel locked and is braking. And apply slippage is, let's see here. So there's our slippage right now. Okay, so that takes care of all of that. So after we've gotten all of that, we need angular position. So there's a couple of things we need to do for that. So first off, we need to calculate the angular position. That's based on the omega and delta time. Again, everything needs to be done by the frame rate that's coming in, or the delta time, or actually the speed of the simulation, I should say, since this is not being done on the game thread. This is on the physics thread. So we want the speed of the simulation. So this is omega times that. And then again, this is a plus equal, so and that should give us the angular position. So we're constantly, this is kind of like the wheel's position as it's rotating, and so we're calculating how much position it's moving, and that's all going to be done in radians. And this is the how fast the wheel is going to be moving per tick. And then we have the angular position again based on the integer part. So what we're going to do is we're going to do a modifier, angular position divided by 2 pi, and again that's a constant there by Unreal Engine, and then that's the part that we want. So that's the modifier, and then we multiply that by 2 pi again, and then that should get us the angular position that we actually need. And this angular position is mostly for animation purposes. So this is what's going to be used when we send that to the animation engine for skeletals, or if you're doing statics, you would just use that angular position to figure out how far you want to turn that static wheel on your vehicle. Alright, so again, this is just purely for animation purposes. And then this is the final friction that we've calculated. So again, if we're in contact, if we're not in contact, right? So if we're not in contact, then we have 0 friction. That wheel is going to give us 0 force if it's a powered wheel. Otherwise, if we are in contact, then we just take the final longitudinal, final lateral, and put that into the force form friction there. All right, so that should do it for the simulation part. So next up, let's go ahead and turn our attention to our inputs. So we have some new inputs coming in, and those inputs are going to be used for braking. So we have everything we need for acceleration. So let's go ahead and finish up this video by getting the braking stuff in for inputs, and that will set us up for the next video where we'll then integrate this into our component so that we can now have wheels that can accelerate and brake us. So let's just do that real quick. All right, so all of that data for us is sitting in our vehicle movement traits. So let's bring this up, and we are going to be looking at input. So here we already have some inputs. We've got steering input, transmission type, shifting, throttle input. So let's go ahead and add the wheeled inputs. So I'm going to keep these things separate from the flying input stuff. I know that we have this thing called speed brakes, but I want to keep that more for air braking. So I'm just going to go ahead and add them down here. So what we have, underneath the wheel steering, I'm going to add wheel braking input. So again, this is the us hitting the brake pedal. This is the handbrake if it's one of those ratchet handbrakes where you want to have some braking or a lot of braking. And then this is the parking brake. So if you put it into park, you know, all the wheels will lock depending on how you want to do that. All right, and so that is all going into our vehicle simulation inputs up here. We're going to also, in doing so, we're going to need to go and make a couple of changes. Because these are inputs, we need to add them into our physics network data in case we want to run this over the network. So I'm going to go ahead and we also need to set it into our reset inputs as well. So let's go ahead and take care of that. So I'm just going to go to definition to go pull that up real quick. All right, so upshift, downshift, wheel inputs. So let's go ahead and just finish those off. So let's see. I need these three. Just going to add them there. So again, if I set the reset, set it to 0, set it to 0, and set parking enabled to false. If you want by default parking enabled equals true, you can just set that to true, and that's how that would work. And it would then, but then also if you reset it and it's set to true, right, the simulation will put all the brakes on, and then you'd have to take the parking brake off. Again, up to you on how you want to set things up. Okie dokie. So now let's come down to this. So we don't need to worry about states. We took care of all of that when we were taking care of the tracing in suspension. So we can go ahead and minimize these. And I'm going to go ahead and bring up the input data. So we need apply. No, we need decay. We need net serialization, and we need interpolation. So I'm going to start off with our net serialization. So net serialization, this is going to be what the net physics movement component is going to determine if we're running over the network, whether we need to change the value or not. So again, that's why. So we're doing this bit shift, which is going to create a unique archive value. And if this changes, it means it says, okay, we need to apply the data. Otherwise, if it hasn't changed, it means that we don't have a new value. So we are going to then run either interpolation and decay depending on, and that all depends on, whether, how old the data packet is. So let's go ahead and add this. We just need 3. I'm going to put brake input, handbrake, and parking brake. I'm going to add that down there. Oops. Let's add the A back into the AR. All right, so there's the AR value. So that should take care of net serialization, adding on 3 new inputs. All right, decay. Let's see. That's the decay amount. So again, we're just going to look between the input that's coming in and 0 by the decay amount, which we've decided up here. So we're calculating decay times 2, and then we take a minimum to say, okay, is it, which is it? Is it going to be this value, or which is the smaller number? Is it going to be this value or the decay value, which is coming through? So that's just how we're doing that, and we're just lerping it. So that's for handbrake. That's for handbrake input, as well as for that's for braking handbrake, as well as actually we already have steering input. Do I have one for? Nope, don't need that. And we're only actually going to be lerping the wheel brake and the handbrake because both of these are doubles. We're not going to worry about. We don't need to do anything when it comes to a Boolean value. Boolean values is a state value. It's either on or it's off. So we don't need to worry about decaying that value. And it would be the same, and it's going to be the same thing for, actually, it's not the same thing for here though. So I'm just going to bring it in. So wheel brakes, again, this is our Boolean value. We're going to do a lerp between the, and this is our frame lerp, right? Between the minimum brake and the maximum brake based on our lerp factor, which is being calculated up here. And we have our downshift, upshift, and these are Booleans, so that you can do lerp. We can do this on the Boolean. We're not going to lerp the Boolean, but we can use the lerp factor to determine whether it's, you know, a true or a false. And so we're going to just do the same thing for the parking brake. If you want to do that for the parking brake or not. All right, so that's there. We don't need that. So that should set us up for interpolated data, our decay data, as well as our serialization. So I think we're all good there. All right, so I'm going to go ahead and stop this video here. We're kind of going into over an hour. So I will start up the next video, and in the next video what we'll do is we will then take all the simulation stuff and integrate that into our components, and that should then set us up for, and once that's done, we can then go into our vehicle, since we've handled all the asset stuff, and we should just be able to put some values in, and we should then be able to see our vehicle drive across the desert floor. So, as always, if you like what I'm doing, feel free to like and share my videos, as well as subscribe to my channel. And yeah, I'll see you in the next video. Cheers, and have a great day.